Welcome to this explainer. Have you ever looked at a chemical structure drawn out on a piece of paper and just thought of it as flat? Like just a static two-dimensional drawing that's locked in place forever? Well, today we are going to completely shatter that illusion. We're taking a journey from those flat 2D drawings into the dynamic, constantly shifting, and honestly, surprisingly energetic 3D architecture of molecules. Because organic chemistry isn't just about what atoms are connected to each other, it's about how they behave, how they twist, and how they physically exist in three-dimensional space. Here is our quick roadmap for today. 1. The quest for comfort. 2. The stress of rings. 3. The perfect shape. 4. Drawing the invisible. And finally, number 5, naming the 3D world. All right, let's jump right in. Section 1. The quest for comfort, or as I like to think of it, the lazy molecule. Okay, so to really understand chemistry, you have to understand a deeply relatable concept, which is that molecules are incredibly lazy. Seriously, they're constantly shifting, twisting, and turning, just trying to find the absolute most comfortable, lowest energy position possible. And this brings us to conformational isomers. If you think of a single carbon-carbon bond, not as a rigid steel bar, but more like a freely rotating axle, it makes total sense. Because that axle can spin, the atoms attached to those carbons are constantly changing their positions in space relative to one another. Every slight twist creates a brand new momentary arrangement. Now, there are technically an infinite number of these shapes. We call them conformers, but they definitely aren't all created equal. Some are incredibly comfortable, while others are just extremely stressful. Take ethene, for example. In the eclipsed conformation, imagine being assigned the middle seat on a packed airplane, right between two massive linebackers. You are crammed in, your personal space is completely invaded, and your energy, basically your stress level, is sky high. That's the eclipsed state. The hydrogen atoms on the front carbon are directly blocking or eclipsing the hydrogens on the back carbon, so their electron clouds aggressively repel each other. It's high energy, very unstable. But then you have the staggered conformation. This is the dream. This is like having the entire exit row all to yourself. The atoms are spaced out as far apart as physically possible, repulsion is minimized, energy hits rock bottom, and the molecule is completely, totally relaxed. Charting this rotation for a molecule like butane reveals what is basically a literal energy roller coaster. You'll notice the molecule is naturally drawn to settle in those deep valleys at the bottom. Those are the staggered, comfortable states of maximum stability. But to get from one valley to the next, the molecule has to physically rotate up and over those high-energy peaks, the dreaded, crammed, eclipsed states. The crazy thing is, at room temperature, molecules actually have just enough kinetic energy to push over these peaks, which means they're just constantly tumbling and spinning from one staggered valley to the next. Moving on to Section 2, the stress of rings. Let's talk about forced connections. So what exactly happens when we take those comfortable chains and forcefully bend them into tight loops? Well, we can actually measure this stress or strain by looking at the heat released when the molecule burns. Consider cyclopropane. That's a 3-carbon ring. Normal carbon bonds really want to sit at a nice, relaxed angle of roughly 109.5 degrees. But in a 3-sided ring, geometry violently forces them into tight 60-degree angles. It is literally molecular torture, and you can see the result. The ring strain is a massive 115 kilojoules per mole. But then, check out cyclohexane, the 6-carbon ring. Miraculously, the ring strain plummets all the way down to absolutely zero. Now, this reveals one of the great historical plot twists in organic chemistry. Back in the day, a chemist named Bayer proposed a strain theory based on one massive assumption. He thought all rings lay perfectly flat on a 2D plane. And if rings were truly flat, basic math dictates that cyclopentane, the 5-membered ring, would have bond angles closest to that ideal 109.5 degrees, theoretically making it the most stable. But actual heat of combustion data came along and completely wrecked this theory. Science had to correct itself. The true molecular reality is that rings simply do not stay flat. They pucker, they fold, and they contort into 3-dimensional shapes to relieve stress. And that 3D flexibility is exactly what allows cyclohexane to achieve that magical state of zero strain. Section 3. The perfect shape. Meet the undisputed master of 3D comfort, cyclohexane. If cyclohexane has zero ring strain, how exactly does it pull off this incredible feat? Simply put, by refusing to be a flat hexagon. If it were flat, all its bonds would be forced right back into that terrible, eclipsed, airplane middle seat nightmare. To avoid this, it contorts.
Look at the massive energy penalties for its non-ideal shapes. The half-chair shape sits at a whopping 46 kilojoules per mole. The boat form is slightly better, but it's still highly strained at 28.9, mostly because it suffers from what we call flagpole interactions, where hydrogens essentially crash right into each other. Cyclohexane avoids these high-energy traps whenever it can, overwhelmingly preferring to settle at the very bottom of the energy chart in its perfect zero-strain conformation, the chair.
In that cyclohexane chair, the carbons stagger themselves perfectly to eliminate all strain. But look a little closer at the bonds extending outward. They actually fall into two distinct groups. First, we have the axial bonds. These are the ones pointing straight up and straight down, parallel to the ring's vertical axis. Then we have the equatorial bonds. These point outward, radiating around the perimeter of the ring, kind of like the equator of the Earth. Why does this distinction matter? Well, if you attach a large, bulky group to this ring, it wants some space. If you stick it in the vertical axial position, it's going to awkwardly bump into other vertical atoms in a really cramped interaction. But if you place it in that outward-pointing equatorial position, it has all the room in the world. It's so preferred that molecules will literally flip their entire chair structure inside out just to get their bulkiest groups into that spacious equatorial real estate.
Section 4. Drawing the invisible. This is the classic translator's dilemma. So we know these molecules are 3D, and we know they're constantly contorting, but how on earth do we actually communicate this? I really challenge you to think about this problem. How do you accurately represent a complex, twisting, puckering 3D shape on a totally flat, two-dimensional piece of paper in a way that a chemist on the exact opposite side of the world knows exactly what you mean? You can't just draw flat lines anymore. We needed to invent some highly specialized toolkits.
Our first major tool is the Newman projection. Just imagine picking up a molecule and looking straight down the barrel of a carbon-carbon bond, almost like you're looking through a telescope. The intersection point right in the center, that's your front carbon. The large circle right behind it represents the back carbon. This projection is absolute genius for analyzing molecular comfort because it makes it incredibly easy to spot exactly where atoms are overlapping and eclipsing each other and where they are safely and comfortably staggered.
Now, if you want a slightly wider perspective, you just step back and use the sawhorse projection. Instead of looking straight down the barrel, you view the molecule slightly from above and off to the right. The central bond is drawn diagonally here, which gives you this clear, angled, three-dimensional look at the entire molecule's architecture all at once. You can immediately see the spatial relationship between the front and back groups. And then we have the Fisher projection. Now this one looks like a very simple cross or a grid, but don't let that fool you. There is a strict 3D rule embedded right into these intersecting lines. The rule is elegantly simple. Horizontal lines represent bonds that are physically coming out of the paper to hug you. Vertical lines represent bonds that are fading away from you, retreating back into the distance. It is an incredibly quick, efficient shorthand for drawing highly complex, multi-centered 3D molecules without sketching a tangled mess. Which brings us to Section 5, naming the 3D world, establishing the universal rules.
Once we actually have these 3D architectures mapped out on paper, we desperately need a universal rulebook so we can name them. To do this, chemists use the brilliant logic of the CIP priority rules. It's basically a four-step process. First, you identify a chiral center. That's a carbon atom attached to four completely different groups. Second, you assign priority to those four groups based solely on their atomic number. The heavier the atom, the higher the priority. Simple, right? Third, you mentally rotate the entire 3D molecule so that the lowest priority group, which is usually just a tiny hydrogen atom, is pointing straight away from you, completely in the back. Finally, you draw a mental curve tracing from priority group 1 over to 2 and then to 3. The direction of that mental curve tells you absolutely everything. As you trace from group 1 to 2 to 3, if your path moves clockwise, kind of like turning a steering wheel to the right, the molecule gets the R configuration, from the Latin word rectus for right. If your path traces counterclockwise, like turning the wheel left, it gets the S configuration, from sinister for left. This system is a game changer. It flawlessly translates complex 3D spatial geometry into one simple, universal letter. It's elegant, it's precise, and it completely removes any ambiguity from the conversation. So, we've traveled all the way from the illusion of flat drawings to the messy reality of dynamic 3D molecular acrobatics. We've seen how molecules fold into chairs just to escape strain, and how they spin endlessly around their bonds in this continuous, desperate quest for comfort. Before we wrap up, I want to leave you with a bit of a provocative thought to ponder. If these organic molecules are constantly vibrating, rotating, and flipping to find a better fit, is any chemical structure written on paper truly permanent? Or, when we draw a molecule, are we really just taking a split-second snapshot of a never-ending microscopic dance? Keep that in mind the next time you look at a chemical formula. Thanks so much for joining me on this explainer, and definitely keep exploring the amazing architecture of the invisible world around.